So yesterday the 3A questions were due, and then the 3A discussion. So this week it's all about 3B. So anything on the PowerPoints, anything on the videos from class, anything on the reading. And that's going to be due Sunday at midnight. We do have an exam coming up because we're almost, we're not almost done with this chapter. We just started the second half of it. But our exam is a week from Wednesday is when it's due. So we're going to finish up the 3B this week. And then on Monday will be a review day with the exam being due on Wednesday. I'll open up the exam Sunday in case anyone wants to take it early. But unless we get done with this super early, the review is going to have to wait till Monday. If we have time, we'll start it on Friday.
Okay.
So, all right. So let's continue on with Lewis structures. So with Lewis structures, we're using the handouts, drawing Lewis structure molecules. Okay, so we're going to kind of follow this guideline to help get us there. And we're just going to start with an example. So I'm trying to remember which ones I did last time. I think I wrote them all down. We did CO2, NH3, HCN, arsenic trichloride, calcium tetrachloride. I want to find one that's not an exception. So let's do an exception. Silicon maybe. Okay, let's do this guy. So we learned the last part of the chapter that this is a chemical formula, that the subscripts represent the number of atoms of that element. So there's 1 silicon, 4 bromines. We then took this on to identify it as a covalent or an ionic compound so that we could name it. So silicon, bromine together. So looking at silicon, it's a semi-metal, a metalloid. It's on that zigzag line, it's number 14 on the periodic table. And then bromine's a non-metal. So looking at this, I know it's a covalent because covalents are either non-metals together or semi-metals with non-metals. Okay, so if I name this, I would use prefixes. So this is just a review from last chapter. So let's name it before we draw the structure. Okay? So we're using prefixes, and remember the second element has an IDE ending. So Si is silicon. There's only one of them. Are we going to write monosilicon? No, that was that exception. Remember, if it's the first element present and there's only one, we don't write the mono. We leave off the prefix. So this is silicon. And then there's 4 bromines, so 4 is what prefix? Tetra. Tetra, and then bromine becomes bromide. We've got IDE ending. Good. So we have the structure, we have the name. What else can we do with this chemical formula? We can actually draw a picture of it, place the electrons around it. Okay, so that's what we're going to start with. So using that handout of drawing Lewis structures, the first step is to sketch an outline. So to sketch an outline of that guy, we need to figure out who the central atom is. And it's going to be silicon. It's the least electronegative. It's the first one in the formula. So we'll put silicon in the middle, and then these 4 bromines are going to go around silicon. Okay? We know that bromine, because according to that sheet as well, it doesn't want to be a central atom. It's a halogen. All halogens like to be terminal. So that's why we're not going to pair the bromines up at all. We're just going to put them all around silicon. So now our next step is to count our valence electrons. So we want to see how many we have to play with so that we can try to give everybody their full octet and make them happy. So to calculate the valence electrons, we take the number of atoms and multiply it by the valence electrons. So number of atoms, this part, we get from the subscripts. So the subscripts tell us how many of each. The valence electrons we get from the periodic table, where that element is. So I like to make a list. I have silicon, I have bromine. So how many atoms of silicon?
1.
Just 1. There's no subscript, so we assume it's a 1. How many atoms of bromine?
4.
4, so we're looking at the subscript. So for the valence electrons, now we go to our periodic table and see where it's at. So this is something we covered in the last part of the chapter as well. So silicon's in group 14. So 4, group 14, all of those elements in group 14 have the same number of valence electrons, and that is 4. I just realized I'm drawing this too close together, so I'm going to move them over. Okay, how about bromine? It's a halogen. 7, it's in group 17. It has 7 valence electrons. If it gets just one more, it'll be a noble gas configuration. Okay, so multiply across and add to get the total. So we have 4, 28. So my total is 32. So that means when I go over here, I have 32 electrons that I can use to make everybody happy. I can't use any more, and I can't use any less. I have to use them all. So how do we apply those? Okay, well, first off, these lines that we drew connecting, that's a bond. It's a single bond. And single bonds, we said, were worth 2 electrons. Okay? They're sharing. It's a covalent compound, right? So they're sharing those 2 electrons. So we've already used 2, 4, 6, 8. So we've already used 8. What we want to do with the remainder is we're going to try to make the terminal atoms happy first. That's what it says on the sheet, right? And then we'll worry about the central atom. Okay, so let's start with one of the bromines. So this bromine has a single bond, so it has 2 electrons already. How many does it want? 8. It wants 8. That's that octet that we talked about last part of the chapter. So if it has 2 and it wants 8, how many more do I add? 6. So 2, 4, 6. So I put them as dots. These represent the electrons. That's where we learned about the Lewis dot structures. So we have 2, or 1, 2, so 2, 4, 6, and that single bond counts as the 2 as well, because it's sharing. So 8 total. So we're going to do the same thing to each of the bromines, because they all want 8, just like that bottom one. So add 6 more to each of them. That's a lot of electrons. Okay. So now my terminal atoms are happy. What's going to happen next is we want to make the central atom happy. Is silicon happy right now?
No. Well, yes. It has 8.
Yes, because it's just one.
Because the single bonds count as 2 each. They're sharing them. It's not just bromines, it's both of theirs. So 2, 4, 6, 8. Silicon has 8 too. So now everybody's happy. What I like to do at that point is count my electrons and just make sure I didn't use more than the 32 given. Okay? So 2, 4, 6, 8, and then 8 times 4 gives you 32. So we didn't use more than 32, but we did use all of them. That's the goal. So this is the correct Lewis structure. Okay. All right, we'll try one more with only one central atom, and then we're going to build upon it a little bit, okay? So I don't think I did this one last class. Phosphorus? Hopefully not. Okay, so this is phosphorus trihydride. Just kind of named it already for you. But let's do the structure, the outline. That's how we start when we're drawing these. So who's the central atom? Phosphorus or hydrogen? Phosphorus. So that means those 3 hydrogens are going to go around phosphorus. It doesn't matter wherever you feel like putting them. Just don't put more than one on the side. Okay. So now let's count my valence electrons. Okay. So number of atoms of each. So I have phosphorus and hydrogen. So how many atoms of phosphorus according to the formula? 1. How many atoms of hydrogen according to the formula? 3. Okay, so now we're going to look at the valence electrons. So for that part, we go to the periodic table. So phosphorus is in group 15, so it has 5. Yep. And then hydrogen's in group 1. It just has 1 valence electron. So 5 plus 3. Total would be 8. Okay, at this point it tells us make the terminal atoms happy first. Okay, so the terminal atoms, in this case being hydrogen, are the hydrogens happy?
Yes.
Hydrogen's an exception to the rule. Everybody over here were like, let's give them 8, let's give them 8. Hydrogen just wants 2. That's all it can hold. It has that 1s orbital. It can only hold 2 electrons. So single bonds only for hydrogen, No extra pairs on them. So they're happy. So check, terminal atoms happy, good. Now we worry about phosphorus. So at this point, we're going to count how many electrons we've used. 2, 4, 6, each of these is 2 electrons, so we've used 2, 4, 6. Okay, so I've used 6 of my 8. What that means is I have 2 electrons left. So what do you think I'm going to do with those? Does phosphorus need more?
Yes.
How many does phosphorus want?
8.
8. And we just said, has 2, 4, 6 because of those single bonds. So we're going to take those last 2 and just pop them right on top. Now he has 2, 4, 6, and then that lone pair counts as 2 as well. So he has 8 total electrons, which is good because we had to use those somewhere because we have 8 total to use. So it makes sense that he needed more. Yeah. All right. So now let's try an example where there's more than one central atom. And most of these examples are going to be carbon examples, because carbons like to make chains. So let's start with C2H4. Dicarbon tetrahydride. I'll get some practice with the name. We don't want to forget about that. All right, so when we're drawing the structure, what do you think the central atom is going to be, carbon or hydrogen?
Carbon.
Carbon, but this time there's more than one. So what happens in that case? Well, with carbons, they like to make chains. What that means is they like to be attached to each other. Okay, so if I had 3 or even 5 carbons, I would just keep making a carbon chain. All right, but in this case, I just have 2, so I'm stopping there. Well, how do I know where those 4 hydrogens go? Do I put 3 on one, 1 on the other? Like, how does that work? Well, in nature, symmetry usually wins. You can see that when you look at a leaf, when you look at a snowflake, right? Things are usually want to be symmetrical. So do that. Put 2 on each. Share. I mean, it's a covalent compound, that's what they do, right? They share. So let's do a hydrogen here, hydrogen here. And it doesn't matter if you put yours down there. Okay, we're not getting into the shapes quite yet, so wherever you happen to put them, it's fine. So I've used the 2 carbons and the 4 hydrogens, sharing them equally. So let's see how many valence electrons we have, and then try to make everybody happy. So make our list. We have carbon and hydrogen. So the number of atoms of carbon, 2. We're looking at the subscript here, so 2 atoms. And then multiply that by the valence electrons. 4, yeah, it does have 4, doesn't it? It's in group 14, so it has 4 valence electrons. I didn't know if you were answering this one or the number of atoms of hydrogen. So how many atoms of hydrogen?
4.
That one's 4. So it's little. And then the valence electrons? 1. It's in group 1, so it has just that 1 valence electron. So multiply and add for the total. So we have 8 plus 4, so it's 12 total. Okay. So doing this one, we want to make the terminal atoms happy first. And terminal being the hydrogens, because both of these carbon are both central. So are the hydrogens happy?
Yes.
Yes. Okay, so to make the central atoms happy, we need to see what we have left. So how many have we used?
2, 4, 6, 8, 10.
So we've used 10. I've used 10, so that means I have 2 left. Okay. Well, here's the thing. I know I said symmetry, make sure you're sharing, but we cannot put 1 electron on each. That's incorrect. So the reason that's incorrect is when 1 electron's by itself, it's called a radical, and it's a very, very unstable molecule. So when we have electrons and we add them, we're always going to put them in a pair. So we're always going to keep them together. And I know that's counterintuitive because I said they're electrons, they want to be as far apart as possible. But we don't want to separate them onto 2 separate atoms and create that unstable radical. So we're going to just pick one. Since we only have 2 and we can't split them, just pick one of the carbons to put them on. Okay, so I'm going to pick this one. You pick the other one, that's fine, because we're going to be changing it in a second anyway. what this does is this carbon on to the left, how many electrons does he have? Now that I added that pair.
8,
8. 2, 4, 6, 8. But how many carbons does this guy have?
6.
6. But I have none left to give him, right? So if I want to make him happy, my only next step, if you look at the list, is if you have no more electrons to give, that's when you start doing the double and triple bonds. So what that means is I can take this pair, because we can't do a double bond between hydrogen and carbon, because hydrogen can only have 2 electrons.
Put it in the middle.
So we're going to have to put it in the middle, right? So in order to do a double bond, we need a lone pair somewhere. This is the only lone pair in the picture, so we know that this is going to make a double bond somewhere. The question is where? Well, it's not going to help us to make a double bond here, or to make a double bond between this carbon and hydrogen. It's only going to help if I put it here, because this is the carbon that's unhappy. This is the carbon that needs more. So if I take that that lone pair, so those 2 electrons, remember, a bond is equal to 2 electrons. So I can make a double bond with those 2. So that's going to give me a double bond between the carbons, and then I still have the hydrogens on both sides. So this would be the correct Lewis structure. And it's still symmetrical, right? In the end, it ended up being symmetrical, even though I had to choose a carbon to put that lone pair on for a second. Should we try another one with more than one?
Yes.
And maybe we'll try a polyatomic with some charges. So there's one similar to this on the homework I saw, and I thought this might be confusing for some people, so I wanted to do one like this. It's written a little different. It's the way organic molecules are written. So I wanted to explain it. All right, so to draw the outline of that structure, what's going to be my central atoms? Carbon, hydrogen, or oxygen?
Carbon and oxygen.
It is going to end up being carbon and oxygen, but you would start with carbon because it's the least electronegative. And I just said over here, carbon likes to make chains. So if you see more than one carbon, just start by making a chain of all the carbons. For this course, it changes if you went into organic chemistry, you will always see carbons in a chain. Okay, so now I have 7 hydrogens and I have this OH over here. Okay, why does it not say H8O? Why is that hydrogen over there? Because it's trying to tell you that this belongs together. That's that hydroxide ion that we saw. That's one of the polyatomics. This is a covalent compound, but I'm just telling you that that belongs together. Okay, so what I would do with this is I would pick one of the terminal carbons to put it on, one of the outside ones. Okay, and then I would take the rest, so this is what I have left, my 7 hydrogens, and try to put them on here as evenly as possible. Okay, well, say I put 2 on each, that's how I'm going to start. Because I said spread them, right? So I got 2, I have 4, I have 6. Okay, but I have 7 hydrogens that I need to use. Where do you think that last one's going to go?
To the other side.
It has to go here. So how do you know that? Look at this carbon. How many electrons does it have around it? 8. So I can't possibly put any more on him. Right? This carbon, 8. He can't have more than that. This carbon has 6. So it makes sense that I could add the last hydrogen here to make him happy. It's going to get complicated. So you know how I put that OH? I'm going to draw a line with the H because they are bonded together. Once we add our valence electrons. This is one of the hardest ones you'll see. There's only one like this, so bear with me. Valence electron count. Let's do that. We have a lot of electrons involved here, right? We have carbons, we have hydrogens, and we have oxygens. So total carbon atoms.
Carbon is 3.
Yep, we're looking at the formula. The hydrogen's tricky because you have 7 here, but you can't forget about that one. So how many total hydrogens? 8, because we can put them together when we're trying to figure out just how many. And then oxygen, just 1. There's no subscript after it, so it's just 1. So now we find the valence electrons in each according to the periodic table. Carbon's in group 14, so it has 4. That's shield. 8 hydrogens, and they have 1, because they're in group 1. Oxygen has how many?
6.
6. It's in group 16. Good. So we got 12 plus 8 gives me 20. 8 plus 6. So 26. Tell me if I added wrong. Well, when we went through to draw it, we already discovered that, hey, these 3 carbons are happy, right? Are my terminal atoms happy? Are all my hydrogens happy?
No.
How many?
Yes.
No, yes, which one?
Yes, they all have 2.
Yeah, the hydrogens only want 2. So anytime you see hydrogen with a single bond, it's happy. Don't do anything else to it. Don't make a double bond. Don't put any extra electrons on it. All it wants is a single bond. That's it. So all of these hydrogens have a single bond, so we're not going to do anything to them. So who's the only atom here that's not happy?
Oxygen.
Oxygen. He has how many?
4.
4, and he wants
8.
He wants 8 like everybody else. So let's see how we're going to do that, because we want to make sure we have enough electrons to put on him. Because what I want to do is just do 2 lone pairs, but can I? So how many have we used? 22? So I counted, so I've used 22, so I do have 4 left. Okay? And we just said oxygen has 4, that means he wants 4 more, so perfect. I can just throw it on there. So this would be the correct Lewis structure. If you count all the electrons now, you will count a total of 26, which is what we had originally. And one thing about oxygen, and I don't think I've done this one yet, if you look at its Lewis dot structure, we said it has 6 valence electrons, because it's in group 16, agreed? So if I draw just its Lewis dot structure, 2, 4, 5, and 6. So with the Lewis dot structures, the unpaired electrons, those are the ones that like to make bonds. So that means oxygen likes to make 2 bonds, and it likes to have 2 pairs, 2 electron pairs, and it does. So almost every time you draw these, with the exception of an ion, this is what it's going to look like. It's going to have 2 bonds and 2 lone pairs. So those Lewis dot structures at the very beginning of chapter 3D will kind of help you figure out how many bonds does that atom like to make, how many electron pairs does that atom like to have. You'll see a trend there, because carbon likes the same thing. Carbon has 4 valence electrons, so that means it has 4 unpaired electrons. So carbon likes to make 4 bonds. 1, 2, 3, 4. It did make 4 bonds, right? It has no electron pairs on it because it doesn't have any electron pairs on it in its Lewis dot structure. All right, should we try an ion? Polyatomics? We're going to be able to draw those, and then we're going to be able to figure out the shape. And in lab, we're actually going to build the shape. 3D, pretty cool. Depending on your definition of cool. All right. So
this is a polyatomic ion.
yes, now we're doing polyatomic ions. If I can get my marker open. It's just polyatomic. So let's do CO3, the 2 minus. Okay. So let's start with the structure like we've been doing. So who's central, carbon or oxygen?
Carbon.
Carbon, it's usually the first one. So we have carbon, and then we have 3 oxygens around it. So I would start with just single bonds, because you don't want to do a double or triple bond unless you have to. So this is my basic structure, but now I need to count the valence electrons. And this is the tricky part with ions, okay? Because this 2 minus is going to affect our count. So we're going to have to take that into account at the end. But let's start by calculating how we normally do, by writing the atoms present, how many of each, and then their valence electrons. So carbon, how many atoms? 1, valence electrons? 4. See, by the time you're done with this, you're going to memorize those without even looking at the periodic table. Oxygen's in group 16.
6,
6, and I skipped a step. How many atoms?
3.
3. So the atoms, we're looking at the chemical formula itself. The valence electrons were from the periodic table. So I'm not done, so I'm not going to draw a line and add it, because I have to take into account this 2 minus here. So what does that 2 minus tell me? Does that mean that I lost 2 electrons or that I gained 2?
Okay.
Gained, because electrons are negatively charged. So what I need to do is add 2 more to this. Because that means I have 2 extra on top of what carbon and oxygen are bringing to the group. And we'll do a positive ion next so you can see how that looks. But let's start here. So 4 plus 18 is plus 2, is that 24? Because 18 plus 2 is 20, and plus 1 more, yeah. So now let's distribute. Remember, terminal atoms happy first. So each oxygen has how many right now? 2 because of the single bond, so we're going to add how many more? 6. So 2, 4, 6. So do that to all of them. All right, so oxygens are happy. Now we worry about the central atom. Is the central atom carbon happy?
No.
How many does he have right now?
6.
6. Each bond is 2. So before we go throwing an electron pair on him, let's see if we have any extras to put. So how many have we used so far? 8 here, 8, and 8. So we've used 24, right? 2, 4, 6, 8, 8 times 3, 24. We have nothing left. So that means we got nothing to put on him. When that happens, what you need to do is, it's the very last step, step number 6. If the central atom lacks an octet, you can move 1 or more lone pairs from an outer atom to make a double or triple bond. So that's what we're going to do. It's the last step because this is your last resort. You don't want to do a double or triple if you don't have to. They're higher in energy. They're harder to make, harder to break. So it doesn't matter which atom you choose, okay? Pick one, make a double bond. If you did the top one or the other one, that's fine. By resonance, all of them are correct. And we're not even going to get into resonance, but in case you're curious, that's why all of them are correct. So, O. Okay, so now carbon, 2, 4, 6, 8. He's happy. We've only used the 24 allowed. Remember, when you move to make that a double bond, you only have 2 electron pairs on this oxygen now. If you keep it at 3, he's going to have more than he can handle. Now, if someone's looking at this structure, they're going to wonder why you have 2 extra electrons on here. So when you're done with the structure, you need to put brackets around it and the charge on the outside. So the only time you do the brackets is when it's an ion. Because if I were looking at this, I would be counting your electrons and going, where did they get those 2 extra? So we need to indicate that by putting the charge there, so the person looking at it goes, oh, they got it because it's an ion. And this is very important. We're doing a lab where we're drawing a whole bunch of these, so make sure you're doing the brackets with the charge for the ions that you do. Okay? And that's lab 8, so that's a ways away still. All right, should we try another ion, but with a positive?
Yes.
So this is the only positive polyatomic I have on the chart that I gave you, so we're going to do that one, ammonium, NH4+. So we're going to go through the same steps. We're going to start by treating it like it doesn't have a charge. We're going to draw the structure of it. So central atom is nitrogen, terminal atoms with then hydrogen. So put all 4 around him. This one's actually probably easier than it looks. So now let's figure out how many valence electrons we have. So we have nitrogen, hydrogen.
1 atom.
1 atom of nitrogen.
5 valence, 4.
5 valence electrons. Is it in group 15? Yes, it is. So group 15 has 5.
Hydrogen
4 atoms and
1.
for a total of, oops, I just made a mistake for a total of, but it has a charge. So I got to take into account the charge. Over here I added because it was negative. I had 2 extra. This time it's positive. That means they took one of these away. It's gonna have to be 8, because I'm gonna subtract 1 valence electron. Because we have 9 here, right?
Oh, it's
But they
just a
took
plus.
1 away,
Mhm.
so I only have 8. That's why I have a positive. They took one of those 9 that I originally had away from me. All right, how many electrons have I used?
2, 4, 6, 8.
8. Is everybody happy?
Yes.
So the only thing I have left to do is
With your brackets.
my brackets. Because if someone looked at this, they would wonder why you don't have that extra electron somewhere. Notice all our electron counts are even numbers because we use them in pairs.
Mhm.
Okay, so if you ever get an odd number, look back. Something went wrong. Well, clue there. Guys starting to get the hang of it?
Mhm.
Okay, so now let me confuse you. I'm going to do exceptions. You know, there's exceptions to everything we've talked about in this course. There's exceptions to the octet rule as well. So that's what we're going to look at next, is exceptions. And we talked about one of the exceptions already, right? Hydrogen and helium. They only want 2. Shouldn't write valence electrons. Oh yeah, okay. So they're already an exception, because the octet rule says everybody wants 8. So we're going to look at some Lewis structures who are exceptions. So let's start by just drawing them, and you'll see where the exception applies. Aluminum trichloride. So, central atoms, going to be aluminum, first one in the list here. Also the least electronegative. And then we have 3 chlorines. So we'll just put it around that. And count our valence electrons. So we have aluminum, we have chlorine. 1 aluminum, and it's a group of 13, so 3 valence electrons. Chlorine, 3 atoms, and it's a halogen. All halogens have
7.
7. So I get 7 times 3 is 21, plus 3 more, 26. Did I count that wrong?
Yeah.
24. Thank you. See? This is why I need people in the class. Imagine if they're not in class, how many mistakes I've made. All right, so terminal atoms happy first. So, how many does each chlorine need added to it? 6, because if each chlorine has 2 right now, they want an octet, so we're going to make them happy by giving them 6 each. So now each chlorine has a total of 8. All right, aluminum. Is aluminum happy according to the octet rule? No. Okay, well, let's see how many electrons we've used. I think we've used all 24, right? 2, 4, 6, 8, 8 times 3. So I've used all 24. So we get to this step where we have no more to give the central guy, and this is usually where we make our double bond, right? Look at your sheet, and I really hope I wrote it on there. Maybe I didn't. Hydrogen and the halogens do not make double bonds. Hydrogens and halogens only make single bonds. So hydrogen and halogen, single bonds only. They will not make a double. Hydrogen for obvious reasons, because it can't. It physically does not have the room. Halogens, well, I'm going to point you to their Lewis structure to explain that one. We said a halogen, or chlorine in particular, had 7 valence electrons, correct? So this is what it would look like, 2, 4, 6, and then the 7. So it has 1 unpaired electron, so that means it's going to make just 1 single bond. We're not going to see it make a double. So I'm not going to take one of these pairs and make a double. That's incorrect. This is the correct Lewis structure as is. Why? Because this is one of our exceptions. So over here, I'll write the exceptions. We have aluminum and boron. Notice they're both in group 13. You could even add gallium in there in case we ever see him, because he's in group 13 as well. So these elements, they're happy with 6. And we're going to do another example so you can see that as well. In this picture here, aluminum has 2, 4, 6. He's happy. If you look at aluminum's electron dot configuration, he has 3 valence electrons. So notice he wants to make 3 single bonds, but he doesn't want a lone pair on him. So you're never going to see a lone pair on aluminum. You're never going to see aluminum with a double bond. Same with boron, same with gallium, because they're in the same row. They're going to follow the same trends that aluminum does. So let's apply this to try one more. Let's do BH3. So, we have boron in the middle, and then 3 hydrogens. So boron, hydrogen. So number of atoms, we have 1 boron, we have 3 hydrogens. We just said boron has 3 valence electrons, just like aluminum. And hydrogen has 1. I'm done. That's a nice thing about some of the exceptions, especially this one. Because hydrogens are happy, they only want 2. Boron, he's an exception, so he only wants 6. And we couldn't give him more if we wanted to, because hydrogen definitely is not going to do a double bond. Because it can't, it doesn't have the room. And there's no extra electrons to make it and do that. We've already used the 6 allowed. So this is the correct structure. So the first exception is that aluminum, boron, gallium are happy with 6. There's one more exception. And that is the expanded octet. That means is they can have more than 8 valence electrons. So over here we saw some that are happy with less than 8. Now we're going to look at the ones that are happy with more than 8. And this can only happen for elements in period. Remember, periods are going across 3 on up. So those principal quantum numbers, 3 on up. So I'm looking at row 3 where sodium starts, and then row 4 with potassium, row 5 all the way across like that. Okay, so let's look at an example of this. We have, I mean you have one actually in your picture there, but let's not do that one then. I didn't put that as an example. So what I'm referring to is on that drawing Lewis structures at the very bottom. It shows an example of this with a sulfur, how many coins are that? Hexachloride compound. So we'll do a different example. Let's look at PF5. So phosphorus pentafluoride. So our central atom is P, phosphorus. Now these 5 fluorines, they're going to all go around phosphorus. But you'll notice, right when we do that, you're kind of probably thinking, where does that extra one go? Because if we have single bonds, which we have to have at least a single bond, how many electrons does phosphorus have right now?
2, 4, 6, 8, 10.
He already has more than 8. And so at first you might be like, oh no, do I need to go and start doing something crazy like that? No, don't do that. Fluorine's a halogen. We said they only want 1 single bond. So this is why this is incorrect. Okay? Why can we do this though? Because of this exception. Elements in period 3+ can expand their octet. That's because of those d orbitals they have. That's why we called it the 3d instead of 4d. They can throw them in there. Okay? They have that extra space. So looking at phosphorus, it is in period 3. So we can do this. All right? Now to finish the drawing though, we know that phosphorus is more than happy, but are the fluorines? Not yet. So we still need to do our process and figure out our total. So phosphorus is just 1, fluorines 5. Phosphorus is group 15, right? So group 15 has 5 valence electrons. Halogens all have 7. So 35 plus, that is 35, right? So that's 40. That's our highest count so far. But that's because, how are we going to make these fluorines happy? How many more electrons do we need to add to each one?
6 each.
6 to each one. They have 2 each with that single bond. So now we have to go and draw a lot of dots. So 2, 4, 6, 8, and we have 5 of them. So 8 times 5 is my total of 40. So that's done. I want to show one more before we go, just to, because you might not expect it looking at the chemical formula. Is it chlorine? It was fluorine again. You could do chlorine, just be different. Okay. So it's sulfur tetrachloride. So sulfur central, chlorines go around. We're starting to get the hang of this, right? So I'm going to kind of go a little faster. Next step is to do your valence electrons. We have sulfur, we have chlorine. Numbers of atoms of each, we have 1 and 4. Valence electrons, so sulfur's in group 16, so it's going to have 6. Chlorine is a halogen, so it's going to have 7. All halogens have 7. So what is 28 plus 6? 7 times 4 is 28, plus 6 more is 34. Correct me if I'm wrong. It is Monday. Okay. What's the next step?
See how many we got already and make chlorine happy.
Yep, so we want to make chlorines happy. I mean, we've used 8, but our goal is terminal atoms happy first, then we worry about the central diet. So we're adding 6 to each chlorine, much like we did in the last example, for a total of 8 each. Okay, so the chlorines are happy. Is sulfur happy? Okay, but always check. Make sure you used all the electrons. 2, 4, 6, 8. So what's 8 times 4? 32. I've only used 32. That means I have 2 left. Where am I going to put them? Because I have to use them all. I can't just say, oh, I don't need those. No, they're part of it. So in this case, we can't add them to chlorine, because chlorine's in period 2. But is sulfur in period 3 or higher? It's right next to phosphorus. So that means it can have an expanded octet, so we can add them onto sulfur. So that's exactly what you do. You would put a pair on sulfur. Now sulfur has 10, but that's okay. So keep these notes for Wednesday, whether you come in class or watch the video, because what we're going to do with all these shapes, instead of redrawing them, is we're going to use the packet here to figure out what the shape is, the 3D shape. So I'm going to be drawing all of these on the board at the beginning of class, and we're going to go through and use this to classify them as the correct shape. Okay? Awesome. Guys have any questions?